In this mini lecture, we will discuss atomic structure and ways of expressing the composition of an atom using atomic symbols. As we saw from our history lesson on the atom, modern atomic structure describes the nucleus as very small and very dense compared to the rest of the volume of the atom, which is mostly comprised of empty space that is thinly populated by electrons. We can see from the sizes marked in this figure that the diameter of the nucleus is about 4 to 5 orders of magnitude smaller than the diameter of the atom. To get a better sense of that difference in scale, I like to use the analogy that if the atom was the size of a baseball stadium, then the nucleus would be the size of a fly, positioned roughly in the center of the stadium on the pitcher's mound. The reason the nucleus is so dense is because the incredibly small volume of the nucleus contains practically the entire mass of the atom. Note in this chart that the mass of a proton and a neutron are about the same and are both 4 orders of magnitude larger than the mass of an electron. Protons and neutrons are both found in the nucleus, while electrons are found in the empty space outside the nucleus. Since the protons and neutrons are so much heavier than the electrons, then the total mass of the electrons outside the nucleus will be relatively small compared to the total mass of the protons and neutrons inside the tiny nucleus. Thereby, this makes the nucleus incredibly dense. Protons, neutrons, and electrons are often referred to as subatomic particles as they represent the building blocks of the atom. Note that this modern definition of the atom actually disagrees with Dalton's atomic theory that states that atoms are indivisible and cannot be broken into smaller components. Clearly, we now see that the atoms can theoretically be broken down into these smaller subatomic components, although this is not something that is easy to do for most elements, so Dalton's atomic theory is still practical for the standard conditions of most chemical reactions. Now, the protons in the nucleus play the role of giving an element its chemical identity. If we can change the number of protons in the nucleus, then we have a different element and a whole different set of chemical reactions to deal with. We can start to see why alchemists were unsuccessful at changing lead into gold, because this type of change cannot occur through a chemical reaction. You have to actually change the composition of the nucleus in order to turn lead into gold, as this will require 3 protons to be removed from lead's nucleus. As we can see here that lead has 82 protons, whereas gold only has 79 protons. In an electrically neutral atom, the number of protons in the nucleus is exactly balanced by the number of electrons. This is because protons have positive charges and electrons have negative charges, so neutral elements should have charges that match, as this forms a stable attraction between these subatomic particles. The neutrons in the nucleus play the role of giving an element its isotopic character. Every element has 2 or 3, or actually sometimes even more, different atomic isotopes, where the number of protons is the same in each, but the number of neutrons varies. For 2 atoms to be considered isotopes of the same element, they must have the same number of protons. So as we see below here, these are 3 diagrams showing the 3 most common isotopes of hydrogen. Protium contains 0 neutrons, and it's how we normally think of a hydrogen atom, as being 1 proton and 1 electron. Deuterium contains 1 proton and 1 neutron, while tritium has 2 neutrons. All of these are still considered hydrogen atoms, as they all contain just the 1 proton, and when they're neutral, they are all balanced by just 1 electron. So usually one of the isotopes of an element is more abundant than the others, and for hydrogen, protium happens to be the most abundant isotope, with more than 99.98% of all hydrogen atoms existing as protium. But in terms of chemical reactivity, it's important to remember that all isotopes will react the same way because their protons and electronic structure are the same, so they therefore have the same chemical properties. Therefore, neutrons do not affect the chemical properties of the atom, although they do affect the nuclear properties, but that's a topic for another chapter. The electrons in the nucleus play the role of giving an element what we call its ionic character. As we've seen, if the number of electrons matches the number of protons, then the atom is neutral and it has no ionic character. However, if there are more electrons than protons, we have what's called an anion. And if there are fewer electrons than protons, we have what's called a cation. Throughout this semester, your introduction to chemistry will include a heavy focus on understanding how electrons behave in chemical compounds and what this means for chemical reactions. An atomic symbol includes a superscript and a subscript on the left-hand side of the element symbol, and is how we go about identifying which isotope we're talking about for a particular element. The superscript is the mass number, which represents the sum of the protons and neutrons in the nucleus, which will always be a whole number integer as we simply count these particles and can never have a partial proton or neutron. The subscript is the atomic number, Z, which represents the number of protons only. Therefore, to figure out the number of neutrons in the atom, you only need to subtract the atomic number from the mass number. In the periodic table, elements are arranged based on their atomic numbers, with atomic numbers increasing as we go from left to right in the table and down a column. Since the number of protons indicates the identity of the element and the atomic number indicates the number of protons, then including the atomic number in the atomic symbol is somewhat redundant, as we can simply use the element symbol to look up the element in the periodic table and determine its atomic number. Therefore, isotopes will commonly be labeled with their mass number only, as the atomic number can be determined from the element symbol using a periodic table. We can see this in the example of helium-4 here, where the atomic symbol can be written either with the atomic number of 2, as we see on the left, or without, as the mass number is really the only important bit that needs to be included when referring to a specific isotope of an element. And it's why we often refer to this particular isotope as helium-4, which highlights that mass number. Finally, note that the mass number is not the same as an average atomic mass given on periodic tables, usually below the atomic symbol. The mass number is a whole number integer, and it represents the number of particles in the nucleus. And we saw on a previous slide, those particles do not have masses equal to 1. A proton and a neutron have very specific masses with a lot of sig figs, and they're definitely not equal to 1. So the mass number is not the same thing as the atomic mass. As you can see here, this atomic mass is not a whole number integer. Additionally, each isotope of a particular element can have an entirely different atomic mass due to the differences in the number of neutrons. So the average atomic mass in the periodic table represents a weighted average of those different isotope masses, and it takes into account the relative abundance of each isotope in nature, which means we will never find a single atom of an element or a single isotope that has an atomic mass that perfectly matches the average atomic mass, just due to the nature of how this average atomic mass is defined. However, it's really easy to be confused by all of this because the units of atomic mass have been defined so that the mass number and the atomic mass do kind of turn out to be similar values, particularly for the elements in the first few rows of the periodic table, which are the ones we'll focus on the most in these first two Gen Chem classes. We'll discuss atomic mass in detail in the next mini lecture, so we'll get a little bit better idea of how this whole weighted average of the isotopes actually works. This slide shows an example of how to break down an atomic symbol to determine how many of each subatomic particle it has. For the nitrogen-14 isotope, we know that the atom has 7 protons because it has an atomic number of 7, and if the atom is neutral, that means it'll also have 7 electrons. Since the mass number here is 14, we just subtract the 7 protons to get 7 neutrons for this particular isotope, nitrogen-14. For the nitrogen-15 isotope, we still have the 7 protons because the atom's still nitrogen, and so it's going to have the same atomic number. So that means we'll also still have 7 electrons if the atom is still neutral. However, since the mass number has now increased to 15, this means the number of neutrons has increased to 8 because 15 minus 7 now equals 8. So I hope that kind of clears up how you solve for the number of subatomic particles from these atomic symbols, at least for neutral elements, as we're seeing here. As previously discussed, atoms that are electrically neutral have the same number of protons and electrons. Atoms that contain more protons than electrons, or vice versa, are called ions, and they'll have positive or negative charges based on the comparison of the number of protons and electrons. A cation is an atom that has lost one or more electrons and becomes positively charged. Sodium has an atomic number of 11 and will therefore contain 11 protons, so a neutral sodium atom will also contain 11 electrons. But when sodium gives away one of these electrons, it now becomes a sodium cation with a positive 1 charge because it now has only 10 electrons. So one proton in the nucleus is no longer balanced by an electron, so there's an excess positive charge. Loss of electrons will lead to a decrease in size of the atom as the remaining electrons on the cation do not occupy as much space as in the neutral atom. Now, an anion is an atom that has gained one or more electrons and becomes negatively charged. So chlorine, which has an atomic number of 17, will therefore contain 17 protons. A neutral chlorine atom will also contain 17 electrons. So when chlorine gains an electron, it now becomes a chloride anion with a -1 charge because it now has an extra electron that is no longer balanced by a proton in the nucleus, so there is an excess negative charge. We will discuss ions in detail in future chapters, and we'll even learn why sodium is predisposed to give away one electron, while chlorine prefers to actually gain an electron. This concludes the second mini lecture for Chapter 2. Please note any questions you may have about this material and how it's utilized to solve problems in the sapling homework or end of chapter exercises for this chapter. Please post any urgent questions on Piazza. I will also take questions on this material during one of our virtual class meetings, and during that time, we'll focus more on problem solving for concepts in this chapter.